Good evening, STEM team. In this video, I'll discuss my research findings on automating index selection using machine learning. One of the key concerns in modern data-driven systems is database performance. When such systems grow and develop new connections, queries become more complex and dynamic. Therefore, ensuring fast and efficient query execution is more important than ever. A central mechanism for improving query performance is indexing. Indexes help databases quickly locate and retrieve data without scanning entire tables. While they are not directly accessible to regular users, they can be modified by the system itself and the database administrators. But the challenge is that selecting the optimal set of indexes is a highly complex task. It is not only computationally expensive, but it also involves a wide range of trade-offs. Too few indexes can lead to slow queries, while too many can increase storage costs and slow down data updates. This is where machine learning enters the picture. Machine learning-based approaches to index selection offer the ability to automate indexing by analyzing query workloads, predicting useful indexes, and adapting dynamically to changes without human intervention. There are three main approaches. The first one is supervised learning. The model is first trained on historical workloads. It learns from past examples of queries and their performance with different indexes. Models following this type of learning commonly produce one of the two outputs. We have index-focused models, which classify candidate indexes as useful or not useful, and performance-focused models, which predict continuous metrics like expected query speedup or cost reduction. The strengths of this approach are its accuracy for stable workloads and relatively fast predictions once trained. On the other side, implementation of these models is costly and time-consuming during the training stage. More importantly, these models perform poorly when faced with unseen query patterns or shifting workloads. In practice, this means that they're most suitable for environments with consistent and predictable workloads. The second one is reinforcement learning, which frames index selection as a sequential decision-making problem. In simple terms, the model interacts with the database through making decisions and then observes the effect on performance, adjusting based on the outcomes of own changes. The biggest strength of reinforcement learning is its adaptability to workload changes. The model can dynamically respond to shifting workloads in real time and discover non-obvious index strategies that would not emerge from simple static trial and error. This strength is mainly associated with the learning style of the reinforcement learning model. But this flexibility comes at a cost. Exploration during training can temporarily hurt the performance of a database, and without safety mechanisms like rollback, reinforcement learning models risk introducing harmful indexes into the system. This is one of the key engineering challenges for reinforcement learning-based systems. It is important to supervise the process of system exploration because the model must try different index configurations to learn what works and what causes damages to performance. If a performance degradation I mentioned earlier accidentally happens during peak usage times, the system may experience unacceptable slowdowns and even outages. Therefore, reinforcement learning offers a strong long-term optimization potential, but its deployment requires careful safeguards. Finally, we have industry implementations, where companies like Microsoft, Oracle, and Amazon integrate machine learning-driven automation into production systems. Such commercial adoption of machine learning showcases the evident development of indexing automation in the industry, and it is a great sign for more widespread application of this approach in the future. A leading example that is also widely cited in the related literature is Microsoft Azure SQL. It introduced automatic index tuning in 2016. Unlike traditional advisory tools, Azure SQL creates, drops, and validates indexes automatically. Additionally, it includes regression detection, which means the system monitors whether an index actually improves performance and rolls back the changes if it doesn't. While this cutting-edge technology has numerous advantages, there is little to no information on the process of decision-making in the system. As all the related procedures are processed internally, such lack of transparency reduces trust in automation. Additionally, databases handled by similar systems end up being tied to vendor ecosystems, raising concerns of platform dependence. After any of such models has applied the changes to indexing, it is important to manually evaluate the effect on the system. In research and industry testing, machine learning-driven indexing is usually evaluated with the help of decision support benchmarks. The most commonly used ones are TPCH and TPCDS, which include diverse query types. The key performance indicators, also known as KPIs, include latency reduction and the number of regressions that were successfully detected and rolled back. Both static and dynamic workloads are tested on the system to ensure that the models generalize well and remain robust under changing conditions. Bridging these approaches together, we can identify a set of clear benefits and challenges. The benefits include adaptability, efficiency, scalability, and reduced administrative load. We can clearly trace that the advantages of leveraging machine learning-based approaches lie in major system improvements around time, space, and human resource consumption. As for the challenges, they include training data costs, generalization, transparency issues, and regression risks. These challenges highlight both the promise and the limitations of current machine learning-based indexing systems. They are mainly saturated around less researched areas of optimized training and performance, specifically performance in different environments with unseen queries. My research was centered around the question, to what extent can machine learning automate index selection and what challenges remain? A theoretical solution to this gap was the development of uncertainty-aware indexing models, which would attach confidence levels to their recommendations. This would enable database administrators to weigh the reliability of suggestions, improving trust, safety, and system interpretability. Such advancements would bridge the gap between automation and human oversight. While this idea currently exists only as a concept, it is expected that with the advancements in technology, we will be able to produce a similar model in the near future. Thank you for your attention.